Sure.
Right, welcome everyone again to the afternoon lectures. So today we have yet another new speaker with us, Tracy Slatyer. So I'll just introduce her real quickly. So she obtained her undergraduate degree in physics in 2005 from Australian National University. And then more recently did a PhD at Harvard, completed I think 2010. We share the same advisor, so she's my academic sister in that sense, Douglas Finkbeiner. And after that she did a 3-year postdoc at Princeton. And then became later a professor at MIT in 2013, and then became an associate professor in 2018. During her career, she got many awards. I'll just mention 2. First of all, probably the most relevant to today is Bruno Rossi Prize in 2014, shared with Douglas Finkbeiner and Meng Su on Fermi bubbles. She might mention that in her talks. And
tomorrow, also, maybe, but well, in the public lecture this evening,
public,
but not in these two.
And more recently, 2007 Henry Primakov Award for Early Career Particle Physics from APS. Her research basically covers many aspects of dark matter from both observational and theoretical point of view, and she's here to give 4 lectures on dark matter, so it's a pleasure for us to host her. So let's welcome our speaker.
Well, thank you very much for the kind introduction, Tansu, and thanks very much to all the organizers for inviting me here. I'm unfortunately only able to be here for a few days, but Istanbul is a very beautiful city and this is a very beautiful place. And thanks also to you all for attending the summer school. So yeah, I was asked to talk about dark matter in 4 lectures. So the way that I want to lay this out is my first 2 lectures today are going to be done largely on the whiteboard. I will provide notes for these. They may take a couple of days because I needed to rearrange the lectures at the last minute because my fellow lecturers have already said some of the things that I was planning to say. So I want these first 2 lectures, the questions that I want to really get at is, what do we think we know about dark matter? And in particular, from what we've seen so far, which Tansu told you about last week, what do we think we understand about the microscopic properties of dark matter? You'll see that that's actually a pretty short list, but there are some things that we can say generally. Then, today, I also want to talk about some sort of example benchmark models of dark matter that could potentially explain these properties. These specific models may not be the right answer, but they will give you some examples of the general frameworks that people use to think about these models. If all goes to plan today, then tomorrow I then want to talk about ways that we try to search for dark matter, ways that we try, and you might say, well, we know where dark matter is. Tansu told you where dark matter is. It pervades the universe. It's in large halos around galaxies. So when we talk about searching for dark matter, we usually mean trying to get a handle on its properties as a particle or as something else, trying to understand its nature and its non-gravitational interactions. So today, questions I want to try to answer today are, what do we think we know about the micro properties of DM? And what kind of models can explain them? So, okay, so first, a question for the people at the back. Is this handwriting large enough for you to read? Okay, if at any point during the lecture my handwriting starts shrinking in size and it gets to the point that you can't make out what I'm writing anymore, please wave at me and let me know. Likewise, if I'm talking too softly and you can't hear me anymore, please let me know. Don't sit there politely for half an hour while the lecture is completely incomprehensible, okay? Likewise, please feel free to ask questions as I go. Questions are good. If you're confused about something, there's a very high probability that a significant chunk of the room is also confused about the same thing. So, you know, if something is unclear or you want to understand something better, please speak up. You're doing a favor to other people in the room, okay? Okay, so where do we begin? So this question on what do we know about the micro properties of dark matter? Well, you heard from Tansu that we have reasonably good evidence to believe that the dark matter is cold to a good approximation. It's not super fast moving. I'll say a little bit more about what that teaches us in a little bit, that it's approximately collisionless. If it has interactions, they have to be bounded above by limits from, for example, the bullet cluster or from structure formation, and that it's about 5/6 of the total matter in the universe. These statements seem familiar. If these statements are a deep surprise to anybody, then let me know. And that Tansu talked about dark matter structure formation, so we believe that the way that the universe we observe is formed is that early on, dark matter accreted into this cosmic web, this filamentary structure of dark matter. At the dense points of those structure, we had dark matter halos, which actually provided the seeds for galaxy formation. So in that sense, dark matter is an invisible scaffolding behind the whole universe. So what does this tell us about how it might behave as a microscopic object? So first, what does this statement, the dark matter is cold, actually mean? So the DM has to be pretty cold and slow moving. If the dark matter is too fast moving, then it won't accrete efficiently into small structures. A more precise way of saying that So the more precise way of saying that is that its co-moving free streaming length has to be smaller than a certain value. So this quantity is bounded above. So the notation I'm using here is A, here is the scale factor, V is just the velocity of the dark matter. This is the notation I'm going to be using throughout. Hubble constant, Hubble parameter, which is Z dependent, is H. Redshift is the inverse of the scale factor normalized to today, and this is the Friedman equation. So, and later on I'll be talking about the epochs of radiation domination, when this term dominates the Hubble parameter evolution, matter domination, where this term dominates, and dark energy domination, which occurs at late times and is the epoch that we're currently in. So we'll use these cosmological results a bit later on. But so the statement the dark matter has to be sufficiently slow is basically an upper limit on its velocity through the history of the universe. If the dark matter can move too fast, it will erase structures smaller than this free streaming length. So this is bounded above by observations of the smallest structures. So this, in principle, doesn't tell us that much about dark matter's particle nature without other assumptions, because dark matter could be a very wide range of possibilities and still be pretty slow moving. But it gives you some information on how strongly it can have talked to the visible matter in the early universe, because we know how hot the visible matter is. We know how much kinetic energy the visible matter has. If the dark matter was the same temperature as the visible matter at some point, that would give it some non-trivial velocity. Question in the back.
Do we mean that it's slow moving? Like it's not have to behave like a relativistic particle?
So the constraint is when, right? Like, so it's definitely true that dark matter, like at late times, to when structure was forming, had better not be traveling at the speed of light. But the constraint is actually a little bit stronger than that. The constraint is really just that if you integrate over all times, how fast was the dark matter going? You know, how much co-moving distance did this free streaming erase? It has to be a small enough distance that we haven't yet probed it observationally. And as we get better and better observational probes of small scales, which I think Tansu told you about in his previous lectures, this bound can potentially get tighter and tighter. Okay? So if the way that this is usually stated is a bound on warm dark matter, the way that requires an extra assumption, which is if the dark matter was once in full thermal contact with the standard model, so it was in thermal equilibrium, it had the same temperature as the standard model. And at the time that it decoupled, it was going at the speed of light or close to it. then you know exactly how much momentum the dark matter has. Like at the time it decoupled, it had the momentum of relativistic species at the same temperature as the standard model. And so at later times, its velocity just depends entirely on its mass. And you can predict, and you can relate the mass and its velocity in this scenario. So in that case, this integral ends up mostly being dominated by when the dark matter was going at a relativistic speed. So then this basically becomes a limit on when was the dark matter last relativistic. But it depends on the mass because its mass determines when it stops being relativistic. It's a function of its temperature. Okay, so if the dark matter was once in full thermal equilibrium with the standard model and decoupled while relativistic, then the dm momentum is just similar to the visible photon momentum at late times. The V history is set by the dm mass, which I'll call mdm. And in that case, your upper limit on V turns into a lower limit on m. If dark matter's lighter, it stays relativistic for longer. You end up running into this bound faster. So this gives you, so the upper limit on V equals lower limit on m. So that gives us our first sort of quasi-model independent constraint. It relies on this assumption about it being in thermal equilibrium, but if you have any dark matter model in that category, which I'll call thermal dm, this implies that the dark matter mass is greater than about 5 keV. Now, there are some debates about, you can change this number by a little bit depending on exactly what assumptions you make about the, exactly how you analyze the observations. This comes from bound, from observations of the Lyman alpha forest, which is the clustering of gas at redshifts of about 2 to 6, so when the universe was a factor of 2 to 6 smaller than it is today in linear scales. And this is sometimes called the warm dark matter bound. Okay, so this doesn't really depend on details of how the dark matter interacted with the standard model, or if it's a fermion or a boson or anything like that. It just means that in general, if you heated up the dark matter by contact with the standard model, you want to be above this scale. The main loop, so if you want, another way to say this is, if I want to go to a lower mass than this, I have to violate some of these assumptions. The assumption that you usually violate is that the dark matter was in full thermal contact with the standard model. If the dark matter has very weak interactions with the standard model, it's isolated off in its own sector, then it's perfectly fine for its mass to be lighter than this threshold. Okay, so that's one, so that's one set of constraints that we have. Yeah. Yeah.
I'm not sure there's some sort of interaction with the standard model was supposed to be sufficiently strong in the past in order for these constraints and equilibration to work, but not now.
You only need a very tiny interaction with the standard model to get it into thermal equilibrium with the dark matter in the early universe. Because remember, in the dark matter, in the early universe, the number density is vastly higher than it is today. I mean, so this is telling you how strongly could the dark matter be coupled to the standard model when the temperature of the universe was at the keV scale or higher. The temperature of the universe today is 2.7 Kelvin, which is a few times 10 to the minus 4 eV. So this is temperatures that are, you know, even at the keV scale, we're talking about temperatures that are 7 orders of magnitude higher than they are today. That means density is about 21 orders of magnitude higher than they are today. So you only need I mean, as you'll see, just like weak scale interaction cross sections between dark matter and the standard model are enough to keep the dark matter in full thermal equilibrium with the standard model while the dark matter is relativistic. Once the dark matter abundance starts to drop abruptly, and once the abundances of things it scatters off in the standard model start to drop abruptly, then it becomes harder to stay in equilibrium. But yeah, so this constraint that I'm showing you, this doesn't really set stringent constraints on dark matter that's 100 GeV or so. I mean, for obvious reasons, its mass is so high that even if its momentum is reasonably large, its velocity is very small, and that's what this limit is really constraining. But this is relevant to, for example, sterile neutrinos. In the interactions between sterile neutrinos and visible neutrinos can be very small, but if they're large enough to thermally produce the abundance of the sterile neutrinos, you still tend to fall afoul of this bound. So you need to produce them through a mechanism that keeps the interactions weak enough that you don't need to be in thermal equilibrium. No, good question. Okay, so that's one kind of constraint that we can write down just from looking at these structures. We actually have an even more model-independent and simple constraint from these structures, which is to say that the dark matter can't be too light, or well before you run into this thermal bound, you run into another problem, because if you make the dark matter arbitrarily light, then its de Broglie wavelength can be larger than these small scale structures that we measure. Actually, let me say this another way. Dark matter can't be too light because its de Broglie wavelength must be smaller than the scales of observed structures. If dark matter had a macroscopic de Broglie wavelength, then in general that will suppress structure on scales smaller than the wavelength itself. You have to be able to fit one dark matter particle inside a dwarf galaxy, or inside the dark matter clumps that Tansu has been talking about. So we can work out what limit that imposes on the dark matter mass, and this is the one really hard limit, I know, the really hard lower bound on the dark matter mass. This, again, the strongest bound come from observations of the gas clustering between about redshift 2 to 6. And this requires the dark matter mass to be greater than a few times 10 to the minus 21 electron volts. Now, you'll notice that there's a huge gulf between these two estimates. As soon as we start making model-dependent assumptions like this thermality assumption, we can set much stronger bounds on the range of parameter space that we have to look at. But this is, as far as I know, extremely difficult to escape. So this is our actual concrete lower bound on how light dark matter can possibly be. We can keep going. So if the dark matter is a fermion, then we can set another limit here. Instead of just requiring that you can fit, that the wavelength of the dark matter isn't too large to be contained in the halo, you can work out what's called the Tremaine Gunbound, which comes from the requiring that the Pauli exclusion principle tells you that you can't pack fermions arbitrarily tightly. So can you pack enough fermions into a halo to get the observed density of dark matter in that halo? This is again going to be a lower bound on the mass because we know the mass density pretty well. We don't know the number density that well. So this is sort of our third parametrization. So the Tremaine Gunbound. So this applies to fermion. So the Tremaine Gunbound says that the Pauli exclusion principle sets a bound on the fermionic phase space density. Like if I have my fermions in a condensate, they're all within the Fermi surface, how many can I actually fit into a dwarf galaxy? And you can guess very roughly what this bound is going to look like by saying that the phase space density can parameterize approximately as the number density divided by the typical momentum scale cubed. The number density of the dark matter is the mass density of the dark matter, which we know, divided by its mass. The typical momentum scale for non-relativistic dark matter, which we want to have because we want it to be cold, is roughly MdM times V cubed. And we want that phase space density to be less than or equal to 2 for fermions. Can't have more than 2 fermions, one spin up, one spin down in a given cell. So if I then just rearrange this expression, then what I find is that this gives me, again, a lower bound on the mass that scales with that is determined by the density of the system and the typical velocity of dark matter in the system. We can look at the kind of clumps of dark matter that we know about, the small-scale dwarf galaxies of the Milky Way. And if, for example, I were to plug in a density similar to the local density and a typical velocity comparable to dark matter in dwarf galaxies, about 10 to the minus 5 times c, and plug these numbers in, then what I would find was that this limit is a few hundred eV. So this is very rough, but this is kind of similar to the warm dark matter bound. If dark matter was in thermal contact with the standard model and decoupled while relativistic, it needs to be heavier than about 5 keV. If dark matter is a fermion at all, regardless of its thermal history, if there's only one dark matter species, it needs to be heavier than a few hundred keV. And then there's one more general cosmological bound that I know of on this dark matter parameter space, and that comes from observations of the expansion history. So we have, early in the universe, we have observations of Big Bang nucleosynthesis, which Subir Sarkar is going to tell you a lot about in subsequent lectures. So I'm just going to say that briefly. So Big Bang nucleosynthesis determines the light element abundances today. So this is one probe of the early universe. This corresponds to a temperature of about 1 MeV. And the cosmic microwave background radiation probe's temperatures was released when the temperature of the universe was of order 0.1 eV. These two observables, the CMB radiation and the light element abundances in the present day, these provide our earliest probes of the expansion history. And in particular, both of these can give you a limit on how many species of relativistic particles there are. During the Big Bang nucleosynthesis era, the universe is still heavily radiation dominated. If I change the number of radiation species that I have around, I change the energy density, and hence I change the expansion rate. By the time the CMB is released, the universe is matter dominated, but there's still a non-negligible radiation component, and I still have sensitivity to changes to changes to the expansion rate. So this constrains the density, the energy density of the universe in radiation. So the energy density of the universe in radiation, there's a contribution from photons, and there's a contribution from neutrinos, which we usually write as 3.046 times, I'll write this as rho underscore v. What do I mean by rho v with a bar on it? So this is rho nu with a bar on it. So this is an estimate. This is my own notation. You will not see it in a lot of other places. This is an estimate of the neutrino energy density that you would get if you do a simplified calculation, and it's just the photon energy density times this offset value. Turns out the actual density of any one of the standard model neutrino species is not exactly this number, but it's pretty close. The fact that this prefactor is 3.046 and not 3 is just because this calculation is not quite perfect in getting the neutrino abundance right, but it's pretty good. So these are the radiation sources that we know about. So to parameterize extra sources of radiation, the way that we traditionally write it is as a limit on the number of extra neutrino species under this simplified calculation. But this is really just measuring how much total energy density and radiation do you have in the universe. Now, if any new particles that you have, dark matter or other new particles, have all become deeply non-relativistic by this point, then you don't expect to see anything in this channel. that this is strictly a measurement of light degrees of freedom. But if you have a dark, as I said, the Big Bang nucleosynthesis is probing this parameter at temperatures of around an MeV. So if I have dark matter that is itself non-relativistic, that is itself still relativistic at temperatures of an MeV, or if the dark matter couples to other particles which are or if there are any other particles, they don't have to be the dark matter, that are still relativistic at temperatures of 1 MeV, or if the dark matter particle decays or annihilates and changes the number of relativistic particles around an MeV, all of these effects can leave visible signatures in these measurements. The question there?
I'm sorry, these models are consistent. For example, I mean there is a huge difference between their lower bound.
Yep.
So if they are consistent, we can just put the second one out.
These are all lower bounds, right?
Okay.
I mean, so this is good. So yes, so it is these are inconsistent, but this one has an assumption that this one does not. So I'm going to draw a summary slide, a summary plot as soon as I go through this. But it is always true that essentially, no matter what dark matter candidate you have, no matter what its history, no matter what its interactions with the standard model, its mass scale must be greater than 10 to the minus 21 eV.
That one doesn't have any assumptions.
That one, as far as I can tell, doesn't really have any assumptions in it. You can maybe move this by like a factor of 2 if you change your, if you change the way in which you analyze the data. Well, I mean, if you say, oh, but I have this model that is exactly 2 times 10 to the minus 21 EV, and I'm worried that it's ruled out by this. I mean, you should worry, but I mean, there's some room for flexibility right at the boundary. But this doesn't really have any model-dependent assumptions in it. This has the model-dependent assumption that the dark matter was in thermal contact with the standard model. So this splits you into 2 kinds of categories for dark matter scenarios, where you can have had thermal contact with the standard model, in which case you must be above the multi-keV scale. And in fact, as I'm about to say, BBN and ineffective actually tell you that unless you play some games with model building, you usually have to be above the MeV scale. Because if I had a 5 keV dark matter, okay, that would be fine with these thermal bounds, but it would still be relativistic during BBN. If it was in thermal contact with the standard model, same temperature as the standard model, if the temperature is an MeV and its mass is 5 keV, it would be very relativistic. It would contribute to ineffective, okay? So this tells us there's a thermal range, which is mostly above an MeV and can maybe extend down to 5 keV if you do some work, but it's very hard to push it beyond that. Then there's a non-thermal range, which once you get much below the keV scale, also needs to be a boson. So it can be light, it can be bosonic, it had better not be in thermal contact with the standard model. It has to be cold, it has to be slow moving. And in that regime, you can go down as far as 10 to the minus 21 EV. Does that?
Yes.
Great, thanks. So this limit turns out to be, so again, if the dark matter is very cold, very non-relativistic, very slow moving, then it doesn't matter what its mass is at 1 MeV, provided that it doesn't count as a relativistic species, that its abundance is small, that it doesn't contribute to this radiation energy density, then there's no constraint from this. But again, this bound tells you that any species that did have a significant contribution to the energy density in this temperature range between 0.1 EV and 1 MeV can potentially be constrained. So the actual limit is that BBN tells you, and Subir may have updates on this calculation, so I will just tell you roughly what the constraint is. BBN requires the number of effective degrees of freedom, where remember an effective degree of freedom here is defined as something that behaves like a neutrino, so like a fermion. The number of effective degrees of freedom here has to be less than about 1, and a reference for that.
1 is a good number.
1 is a good number? Okay, very good. Thank you, Subir. So the CMB constraints, so this is a constraint at 1 MeV. The constraint at lower temperatures is significantly stronger, but so the CMB constraint is that N effective, so 3.046 plus delta N effective is equal to 2.99 plus or minus 0.17. And this is from Planck, 2018. So again, this is the MEV scale, this is the 0.1 EV scale. So, you can maybe sneak in an extra degree of freedom if you're only perturbing the radiation density around BBN. Once you get down to the CMB epoch, it starts to become pretty hard to have additional relativistic degrees of freedom. And even at the MEV scale, you should be pretty careful about including extra dark sectors which could have more than one particle in them, or particles with more degrees of freedom than a neutrino. So these constrain new degrees of freedom. Wider than 1 MeV. If the temperature of the dark sector is comparable to the temperature of the standard model. If the dark sector is hotter than the standard model for some reason, this constraint gets stronger. The energy density in a radiation species scales like its temperature to the power of 4. If the dark sector is colder than the standard model, this is less constrained because rho in radiation scales as the 4th power of temperature. So even if you have a dark sector that's a factor of 2 colder than the standard model, its contribution to the radiation density can be very tiny. But if it's really still at the same temperature of the standard model, so again, in this thermal scenario where the dark matter stays in thermal contact for quite a long time, these limits can be extremely constraining. So broadly speaking, this tells you that if I want thermal DM, then mostly I would like that thermal DM to be heavier than the MEV scale. There are some, there are some loopholes in this constraint. For example, there's a paper here which shows a situation where the dark matter wasn't in thermal equilibrium with the standard model at early times, comes into thermal equilibrium with the standard model after nucleosynthesis, and then goes back out of thermal equilibrium with the standard model before the CMB epoch. And so if you play a game like this, you can sometimes weasel out of these limits. But in general, dark matter that's in thermal equilibrium with the standard model, it's much easier to get it to work if the dark matter mass is greater than MEV, because otherwise you potentially fall foul of these constraints. Okay, so putting this all together, that's as far as I know, essentially the complete list of limits that are relatively that are sufficiently model independent that I can say them like this in a few sentences, what all the assumptions are that go into getting the bounds. These are limits on the mass of dark matter, on how fast it's moving, and consequently, and on its temperature and on its fermionic versus bosonic nature. So if I try to draw this suggests that if we try to draw the possible mass scales of particle dark matter, where I start at, so I'll start down at 10 to the minus 21 EV, since this is our lower bound, and I'm going to go all the way up to, I'm going to have a bit of a break here, up to the Planck scale. So below this 10 to the minus 21 EV bound, it's just really, I mean, that seems really hard. The dark matter probably cannot be too light. So, and the reason for that is wavelength is too large. But then from there, from 10 to the minus 21 EV, so long as our dark matter is bosonic and is extremely cold, we have many, many orders of magnitude which the dark matter could potentially inhabit as a new particle. So all the way up to, say, the KeV scale. Now below this scale, the dark matter has to be bosonic. the reason that it has to be a bosonic and not a fermion is this argument that if it's a fermion, like if it's a fermion and especially light, then because we know the mass density, we can infer the number density. And the fermions are just too tightly crammed. You need to be able to have something that can be degenerate, that can have an occupation number that's larger than 2 per phase space volume. So yeah, for this very light bosonic matter, you're thinking about it in a condensate situation. That's interesting. So you're wondering, like, so I think that would more apply to if I have fermionic dark matter that's above this boundary, could I still get condensate-like behavior from the fermions forming into Cooper pairs? So there have been, that's an interesting question. My feeling is that once you're above, maybe close to the boundary. In general, the dark matter in the halos is going pretty fast. Like it has a velocity just from the gravitational binding energy of a few hundred kilometers per second. So that seems pretty fast to get into a condensate. But of course, it just depends on the wavelength versus the occupation number. And we know that at the few hundred eV scale, fermionic dark matter in some of these dense, slow-moving systems is getting pretty close to is getting pretty close to having the Fermi sea completely filled. So yeah, maybe in that case you can see condensate-like behavior. But I guess the issue is though there's a wide variety of environments in which we see dark matter, and so if in the densest, slowest moving regions, the fermions are kind of on the boundary of being as densely packed as you can possibly get them, then in galaxies like the Milky Way and the outskirts of those galaxies where the density is lower and the dark matter is going much faster, it probably won't be particularly close to that regime. But yeah, there might be some subregions of the universe where you have close to a fermionic condensate. Thank you, that's a good question. I haven't really, normally when people talk about condensate dark matter, they think about bosons because, then you're not in the boundary. You can go down to 10 to the minus 15 eV objects whose wavelengths are really macroscopic and whose occupation number is pretty large. That's a good question. So down below this case, so in this whole range, so this is 24 orders of magnitude, the dark matter has to be bosonic. Below the KeV scale, it has to be non-thermal due to these velocity bounds as a function of being cold and slow moving. If we go up to the MeV scale, then we have a somewhat less solid bound that says the situation is much easier from a theoretical perspective if it's non-thermal, so that you don't have to worry about these potential extra degrees of freedom measured in BBN or the CMB. Okay, so below the KeV to MeV scale and all the way down to here, we have some picture of what dark matter should look like. It should be a boson. In the lower part of this, it will have a very high occupation number. It should be cold. It should not have been in thermal contact with the standard model. So this actually tells us quite a lot about its history and constrains what kind of dark matter options we could have. Above the MeV scale, in contrast, the field is much more open. So above the MeV scale, it can have a thermal history, and that's fine. It's cool enough by BBN. Maybe this is 10 MeV. That starts to become model dependent. But broadly speaking, above this scale, the dark matter will be non-relativistic. By BBN, it will be non-relativistic through the epoch of structure formation. Its velocity will be low enough that you don't erase small-scale structure to a meaningful degree. And I'll show you in a moment that in this range, it's not that hard to have the abundance of dark matter be set by its interactions with the standard model bath that are the same things that keep it thermal. So we sometimes draw from the MeV scale up to about the 100 TeV scale the thermal window. Why does it end at 100 TeV? It's because the simplest way of getting the dark matter abundance right, as I'll show you, stops working through these interactions with the standard model, stops working at about 100 TeV. I haven't justified that to you yet. That will come momentarily. Now, within this window, the region that's gotten the most interest in terms of dark matter searches is this GeV to TeV range which is the classic WIMP, or weakly interacting massive particle window. So I'll talk in my lectures tomorrow about a range of searches that have occurred and that are still ongoing in this region. Part of the reason this got so much attention is because this is a region that we can attack experimentally from multiple fronts. We could hope to get confirming pieces of evidence from different experiments that would allow us to put together the puzzle of what's going on here. And another reason is that this is the ballpark in which you might expect a dark matter candidate to live if you had a supersymmetric theory of physics beyond the standard model. So those two motivated a lot of work in this area. But in recent years, people have essentially sort of looked back at these arguments and said, well, the thermal window is actually significantly broader than this GeV to TeV range. Let's see what we can do to try to probe dark matter particles across this full range. And in addition to that, people have also said, well, and the thermal window is only a tiny fraction of the space available. If we look at this in sort of log degrees of freedom, the thermal window has the advantages. I'll show you that it's pretty easy to get the dark matter density right, and it can have pretty predictive signals, but there's also this enormous space of possibilities down at the low mass end. And at the other end, there are also dark matter candidates that live in this 100 TeV up to M Planck range, so supermassive dark matter candidates. I will not be saying as much about those, not because they're not interesting, but just because they tend to require either the WIMP searches work fine, or they require some pretty idiosyncratic searches that depend strongly on the dark matter candidate itself. And then there's also this part of the spectrum. So, which is maybe dark matter is not a fundamental particle at all. Maybe it's a massively bound state of many smaller particles. Maybe it's something like a primordial black hole. We know from the fact that the CMB detects dark matter, the dark matter had to already be around when the universe was a few 100,000 years old. But maybe the black holes could have been formed in the aftermath of inflation and have just been moving towards us through the universe since then. I'm not going to say that much about this, but though I'm happy to talk about it if people want. But at the moment, my understanding is that there is an open window for primordial black holes to be all the dark matter. It corresponds to roughly mass scales of 10 to the 17 to 10 to the 22 grams. This is about the mass of the bigger asteroids in the asteroid belt. So these are pretty small on black hole scales, but So I mean, we've never detected these objects. It's possible they might have evaded our searches so far. And I'll just give you a reference for how we might go after such black holes. Okay, so as far as I know, that's the best candidate that I know of for non-particle dark matter that wouldn't already have been found at this high scale. So I'm mostly going to focus on particle dark matter for the rest of my discussion, but it's worth keeping in mind that there is a window open that we haven't really probed experimentally yet. Okay, so that's the general layout. Where I want to go next, in my sort of next 10 minutes, and then the second lecture today is to talk you through sort of classic examples of how we get the right abundance of dark matter and how the dark matter behaves in the early universe, both one example in this thermal window and one example in this ultralight, ultracold bosonic dark matter window. Okay, so before I start talking about that, setting up for that, are there any questions to this point? Then let me take the last 5 minutes to set up for the lecture 2. Okay. So I want to first start with this. So now that we've classified dark matter into these general categories, I want to first start with an example in the thermal region. I personally like models in this region because they allow you to naturally tie the abundance of dark matter to how it interacts with the standard model. This is nice from a conceptual perspective, since the dark matter density is only a factor of a few higher than that of the standard model, and that's a little surprising if they're completely unrelated to each other. And it's attractive from an experimental perspective because it gives you targets to aim for that are not incredibly difficult to see. That doesn't mean it's right, though. It just means it's a possibility. Okay, so the first example I want to do is thermal freeze out. And I want to stress again, like the examples I'm giving you here are not at all exhaustive. They're just two examples of general classes of models which are representative of these two regions. Okay, so the general framework that we'll talk about in the first part of the next lecture is, suppose that the dark matter has some number-changing annihilation reaction. That is, two dark matter particles can come together, and at the end of the interaction, fewer dark matter particles come out than went in. The example that I'm going to work with here, I'm going to assume that's just a two-body interaction, so I'm going to specialize to the case where two dark matter particles come in and some standard model final state particles come out. This does not need to be, and in general will not be just one particle. This could be like a fermion and an antifermion, or a gauge boson or a couple of gauge bosons, or it could be a three-body final state. That doesn't really matter. The point is it's just entirely standard model particles. Now, you can do this in a different way. You can say, suppose it's dark matter plus anti-dark matter. You can redo the calculation in that case. You can, if you have equal amounts of dark matter and anti-dark matter, the calculation is very similar. If you don't have equal amounts, then it changes in interesting ways. You can have it be the dark matter requires some other particle that is not the dark matter to annihilate against, to reduce its number density. You can have maybe there were 3 dark matter particles in the initial state, not 2. Those processes tend to be pretty suppressed compared to this two-body process, unless the two-body process is forbidden for some reason. So this is kind of the most generic thing. In most models, this is the strongest process, but keep in mind that there are possibilities to do something different. Okay, so then we want to, so the general picture of what's going on here is in the early universe, when at sufficiently early times, this interaction keeps the dark matter and the standard model in equilibrium. So it keeps them at the same temperature. It allows you to freely interconvert back and forth between dark matter and standard model particles. But then we'll see a couple of different cases, but the dark matter, this interaction, so that means that the dark matter, when the dark matter is relativistic, it has the number density of a relativistic species. And it's at the same temperature as the photon bath, so its number density scales roughly as the temperature of the photon bath cubed. So then we have two alternatives. Essentially, this process can become inefficient when the dark matter is still relativistic, or it can become inefficient when the dark matter is no longer relativistic. And we'll see that only the second one of those provides a good candidate for the dark matter. So in this picture, the dark matter is populated in the early universe by the reverse of this interaction. Standard model particles can crash together, make dark matter particles, so you have a very high initial abundance, and then to get the right abundance at late times, this annihilation reaction destroys most of the dark matter, converting it into standard model particles. I guess I have 3 more minutes, so I will, okay, so I will start the setup before we take a break. Okay, so lots of DM early on. Okay, So in order to understand how much dark matter we get at the end, we need to write down how the abundance of dark matter evolves in an expanding universe and in the presence of this annihilation interaction. So let's first do evolution of the DM density. Case 1 will be with no annihilation. So we just turn off the annihilation altogether. There's no number changing processes for the dark matter. So in this case, it's just matter sitting in an expanding universe, and its abundance should just dilute with the expanding volume of the universe. Okay? So in this case, this tells us that the number density times the cube of the scale factor should be equal to 0, because there are no number changing processes. So this just says the total number of dark matter particles is conserved. So we can expand this out. And we divide both sides by a cubed. This gives us, so this n here is the number density of the dark matter. This gives us an equation that looks like this. So this is just saying that the number density of the dark matter changes over time, even if there's no annihilation, just because of the dilution due to the expansion of the universe. So this is dilution from expansion. But now once we turn on annihilation, there's going to be a second dilution process. So another negative term in dn dt. And when we turn on annihilation, we also have to take into account that the reverse process can occur as well, that we can produce dark matter from standard model particles. So we're going to have one term with a positive sign and one term with a negative sign. So let's do the annihilation term first. So with annihilation. So left-hand side will be the same. We just want to add, because there's still going to be this Hubble dilution. So, okay, so then what's our, so our annihilation term? So the rate of annihilation is going to be controlled by some cross-section. We can compute the cross-section from quantum field theory. It's also going to depend on the relative velocity of the dark matter particles, because that controls their flux running into each other. So the total annihilation rate is going to go like this: cross-section times the number density of dark matter squared. This is a depletion term, so it would better have a minus sign. There's actually two other factors. If these are identical particles, there's a 1/2 factor out the front for identical particles. This is just the definition of the cross-section. But each process like this removes 2 dark matter particles from the universe. So this is the annihilation rate, but the rate at which we change NDM is larger than that by a factor of 2. Okay, so that's the, so this is dm, so this is dm goes to x. And then we're going to need the counterpart term, which comes from x goes to dm. And at first you say, oh God, this looks like a pain in the neck. This is going to depend on this is going to depend on the number density of everything in the standard model. How am I going to compute this? So we can use a trick here. So this is production of DM. Okay, so to use this trick, so let's just call this, let's just write this for the moment as the annihilation cross-section times some parameter x. So then what can we say about x? So we can write this whole term as sigma v times x minus n squared. And so what can we say about x? Well, we know, looking at the structure of this equation, if we take this cross-section to be extremely large, then this term will have to be very large. This term will be whatever it is. This difference is going to have to be driven towards 0. So as we make the interaction rate very large, x must approach n squared, or n squared must approach x. But x, this process, it can't depend on the number density of the dark matter. It can only depend on the number density of the standard model particles, right? My rate for 2 standard model particles to collide, it doesn't know about how much dark matter there is present. So So n squared, the dark matter density squared, has to be asymptoting to something equals only. So if we, just from a physical perspective, so you can prove this directly from the Boltzmann equation, but we can just make a physical argument for what has to happen. If we make the cross-section for this process extremely large, it should drive the two systems into equilibrium with each other. It should drive the standard model bath into equilibrium with the dark matter. So a consequence of that is that, so that means that whatever n squared is asymptoting to in this limit has to be the equilibrium value of the dark matter density squared. So this same limit has to drive both n squared towards x and n towards n equilibrium. So that tells us that this x parameter is just the density of the dark matter when it's in thermal equilibrium with the standard model bath, which depends on the temperature of the standard model bath. And so I'll write one equation and then we'll let you take a break. So our final equation that we're going to be dealing with is just that dm by dt plus 3hn equals sigma v squared minus n squared. And this equilibrium distribution is just known. It could be the Fermi-Dirac distribution or the Bose-Einstein distribution. I'm going to assume here that I don't have a high occupation number, and I can just use the Boltzmann distribution for this. But if I do have a really high occupation number and the velocities are low already at this early time, I should strictly be using the Bose-Einstein or Fermi-Dirac distributions. So this n equilibrium, and I'm going to leave out the prefactors because I just want to show you the scaling relations. It's going to go like T cubed when the temperature is much larger than the dark matter mass and the dark matter is relativistic. When the dark matter is non-relativistic, the scaling of this distribution is going to look like this. Okay, so now we could just solve the handed Mathematica, or your favorite computer program, be that Mathematica or Python or some other language. We could just plug this differential equation in, give it the initial conditions that the dark matter starts in thermal equilibrium with the standard model, and then just go ahead and solve this differential equation for n as a function of the temperature of the universe. And that would work fine. So rather than tell you all to do this in Mathematica, when we resume, I'm going to walk through like just how to estimate the scaling relations of what it takes to get the right abundance for dark matter, how that abundance for dark matter depends on this cross-section and on the mass of the dark matter. So I'll do that when we come back. Okay, thanks very much. Are there questions at this time?
It would be appropriate if it was Mathematica, because this equation was first solved by Stephen Wolfram. In 1981.
Really? Okay, I didn't.
It had been solved by Zeldovich back in 1964, but he didn't explain how he solved it.
I see. He just did it. And
Stephen Wolfram wrote his only physics paper when he was in.
and it was solving the
This equation. So then he went on to invent Mathematica.
I see. Well, this is actually ironic because Mathematica has a lot of trouble with this equation today. Like the secret of trying to do this equation in math. So this equation, so we'll talk about this when we resume in 20 minutes. But a feature of this equation, which you can kind of already see just from what we've done, is when the dark matter's in thermal when this cross-section is large in some sense, when these terms on the right are large compared to this Hubble dilution term on the left, then once the dark matter becomes non-relativistic, it's following this exponential scaling with the density. It's dropping off very fast as the temperature of the universe increases. And it's pretty hard for a numerical program to accurately follow that exponential fall off. And then what you're trying to track is what happens once this term becomes small, because it's now exponentially suppressed relative to this term, then you get what we call freeze out, and you transition from this exponential behavior behavior into just this no annihilation behavior. That transition, like especially the exponential fall off, is actually pretty hard for numerical programs to handle, and you usually have to do something a little bit clever to prevent it from complaining at you that your differential equation is very ill conditioned. But yeah, but so modulo that, you can do it in Mathematica. But that's cool. I didn't know that Wolfram did this. Okay, so shall we take a break and reconvene in 15 minutes?